Hi, I'm Mary, and I'm going to be presenting temporal disentanglement of representations for improved generalisation and reinforcement learning. This is joint work with the co-authors shown here. One important challenge for RL algorithms is that they fail to generalise, especially image-based RL, where a change in just one environment variable, such as the background colour, can change many pixels in the image, which in turn can change the entire representation of the image that the agent learned in training. This means a policy based on this representation is no longer optimal after a change in the environment, which can be seen in the cartpole swing up example here. Often the agent has to retrain from scratch after the change. A promising direction towards more robust RL is to learn a disentangled representation of observations, which aims to separate distinct informative factors of variation in an image into the unknown ground truth factors that generated the image. So for example here we have a set of different images with factors like object shape, colour, background colour, etc. varying in the images. And disentanglement aims to learn a representation that separates out these factors of variation. If an agent has a representation that's disentangled and it suddenly sees something new, like an object shape it's never seen before, then only that one feature in the representation will be expected to change to something new. Everything else will remain values the agent is already familiar with and can still be relied upon for downstream tasks. However, it's theoretically impossible to learn ground truth factors of variation from IID data alone. But non-IID data is readily available in RL as the image evolves over time. So we propose an approach that uses this temporal structure of RL data to learn a disentangled representation. We propose temporal disentanglement, TED for short, which is an auxiliary task that can be applied to existing RL algorithms. So to explain how it works, I'll build up this architecture diagram, starting here with a standard RL training update. TED is designed to encourage the encoder to uncover the temporal structure determined by observations at consecutive time steps, such that a classifier can discriminate between temporal and non-temporal pairs of representations. So augmenting the diagram with the TED auxiliary task, we also need non-temporal observations. So we sample an observation from a different episode and a non-temporal observation from the same episode. And the representations are used to create three different types of samples: temporal samples, non-temporal different episode samples, and non-temporal same episode samples. These samples are used to train a classifier to discriminate between temporal and non-temporal samples. The structure of the classifier, which is based on permutation contrastive learning, encourages disentanglement by ensuring each feature of the representation is considered separately to the other features, denoted by the superscript I in the equation. This encourages the encoder to uncover the temporal structure necessary for classification by separating the factors of variation into distinct features in the representation. We evaluate our approach on settings where the agent must generalise to unseen values of variables with continued learning on the test environment. We use a training environment with a subset of some of the environment variables, such as colours in the examples here. At the vertical dotted line, we then evaluate generalisation by switching to a test environment with unseen values of the variables and continue training on this test environment. Here we show the results for RAD and SPHERE as two different examples of base algorithms using the TED loss on the DeepMind control suite. The paper also contains results on more tasks and base algorithms. Our results show that TED, in blue, consistently improves the generalisation of the base RL algorithm in orange in all tasks, as well as outperforming state-of-the-art baselines. We also include domain randomisation as a privileged baseline in green, which assumes a test colour set is known in advance, so the agent is trained on the two sets of colours together. And we found in many tasks TED was still able to achieve better performance than domain randomisation because it's more difficult to learn on this larger set of colours. We also evaluated the beta VAE disentanglement metric to measure the extent to which the learned representation is disentangled, and show that TED improves the disentanglement of the base algorithm, where a score of 1 is the highest for a fully disentangled representation. Thank you for listening. Our paper and code are also available online.